Hey, welcome everyone. So I'm Michael Obdenacker. I'm going to talk about, give you an introduction to embedded Linux, in case you're new to that. And a great platform to get started with is a new one, which is called Risc-V. Actually, I'm getting a bit confused with the mix of Roman and Arabic characters. So I could have said this instead, which makes me a little more comfortable, being consistent with the Risc-V naming scheme. So I have to do one thing. You know, the time is limited to XLV minutes today. So before I go ahead and start the presentation, I have lots of things to do in 45 minutes. And because I want to keep 15 minutes for questions as well. So let me quickly go ahead and build a toolchain for this work. So I'll go there. So I need to build a toolchain to compile everything from scratch. So I'm going to go to buildroot.org, download the latest version. Oh, that's the latest version. Well, I haven't tested it yet, so I may play it safe. So it was released like today. Very nice. So let's go to the Risc-V directory, the wget. So I'm going to take the one from August, actually, because that's the one I tested. There we are. So we extract it. I'll repeat this. I run make menu config. And Buildroot is a nice tool to generate a root file system, but also a toolchain. So that's nice. So let's go and select Risc-V as a target architecture. And essentially, the only thing I want to tweak is the target C library. I'll explain that too. So you see it's going to be GCC 9 for the compiler. And I'm going to choose my C library. You can see that only Muscle and glibc are supported at that time. Muscle is a small C library for embedded. I'll cover that in the slides. Right. And since time matters, I'm going to run time make. Time make SDK. In case you don't know that in Buildroot, it's a command that's sufficient to run to create a toolchain. So let's see if it starts. There we are. I hope it's doing the right thing for the right architecture. Okay, now I can get back to the lectures. So I'm Michael Obdenacker. I'm the founder of one of the companies sponsoring this event. We are focused. We are only focusing on embedded Linux and low-level plumbing for Linux. So everything that's low-level enough that works on all architectures, not on all architectures, but that can serve that can be useful to make Linux work on any kind of product. Essentially, so the Linux kernel, the bootloaders, the tools to make the root file systems for embedded Linux, such as the Yocto project and Buildroot, which we contribute to. Myself, I am a contributor to free software too. I'm the current maintainer of the Elixir cross-referencer, which you may know it's a handy way to browse the Linux kernel sources, but also the U-boot sources and many other projects, which are essentially in C and C++. So don't hesitate to try it out. Actually, I'll show some link to it during the slides. And I'm also the co-author of the Bootlin's freely available embedded Linux and kernel training materials that you can find in there. And in a much earlier life, I was also the maintainer of GNU Typist. It's still available, and it's a nice way to learn about typing fast. Not only speaking fast, but typing fast. Typing faster than you can speak. So let's start with the introduction. Why embedded Linux? In case you're new to it. Oops, no, this way. I have to move the camera. So Linux is perfect for to operate devices with a fixed set of features. So unlike on the desktop, Linux, which I mean, you know that the Linux desktop hasn't really taken off yet, but at least in the embedded space, it's almost everywhere. Like it's like almost 99% dominance. It's really ubiquitous. So it's nice to study it and understand it. And the nice thing about embedded Linux is that it's very easy to learn. Unlike Linux itself, which if you approach it from the angle of distribution, it's very complex. There are so many files. But embedded Linux is so much simpler. You can just drop the programs and libraries that you need and see how simple the system can be. So you can understand the usefulness of each file in your file system. And that's what I like in embedded Linux. Another thing is the Linux kernel itself is standalone. So it's easy to study too with that respect. There are no complex dependencies against external software, and all the code is in C. So let's just get the code. If you have a question, just grab, browse, use the editors, and you'll find any piece of source code that you need, because again, the kernel is standalone. So don't be afraid of the kernel either. Linux is nice too because it can work with just a few megabytes of RAM and storage. There's a new version of Linux every 2 to 3 months. And the development community is still relatively small. And if you participate to the community, you end up meeting lots of familiar faces in the conferences, like this one. Unfortunately, I can't see your faces. But if you go to the real life ones, I hope that would be possible soon again. You end up meeting the same people over and over again. And it's like really a feeling of community. And you have many opportunities to become a contributor to the Linux kernel, to bootloader, to the build systems. And there's funding available too, like some companies using Linux are supporting the contributors to those projects, such as we get at Bootlin, we get funding for maintaining some SOCs in the mainline Linux kernel, because it's for everyone's best interest anyway. Oops, sorry. So actually, this presentation is actually an idea to revive an older presentation, which I made 15 years ago. And it was called Embedded Linux from Scratch in 40 minutes. So I took the liberty to add 5 minutes to the presentation because I have a little extra time here. And that presentation was actually showing the boot of a Linux 2.6 kernel on an emulated ARM board for people who don't have some hardware readily available. The name of our company was Free Electrons at that time. And it was one of the most downloaded presentations at that time. So I'm going to try to try that again. So it's also an opportunity to see a few changes that happened since 2015. So in the embedded environment, you have the maker movement. That's definitely new. You have much cheaper development boards. Before, they were 500 euros or more, thousands of euros or dollars. And now you have very attractive ones in the range of 50 to 100 bucks. So that makes the hardware available and affordable for everyone. I should also say that we have observed the rise of open hardware like Arduino, BeagleBone Black, to name a few. So that hardware is actually created in an open way as is software, so people can contribute to it. They can make derivatives. That also is boosting the progress in that area. And something is new too, is the Risc-V, which is a new open source hardware instruction set architecture. So that's what we are going to use in this during this presentation. On the software side, you have the Linux kernel that has made progress, of course, from 2.6.x to 5.x, 5.10 now almost. Git has appeared as well. It was just starting in 2015 in 5. Linux is now everywhere. As I said, you have no money to convince customers to use it, and it's also getting easier and easier to convince them than to fund contributions to the official version. So that's as Bootlin has evolved from the first years to the more recent years, we've seen at the beginning we had to convince people to use Linux, and now we just it's even getting now easier and easier to get the customers to fund the improvements in the official versions of Linux. So we're making very nice progress here. Though it's still a challenge, but more and more people understand the value of participating to the mainline versions of Linux. There's also it's less visible, but there's the advent of devtempfs. Some of you may remember all the stories with devfs and things like that. That was like a monster, and a much cleaner solution. It was created to automatically create the device files. So it makes your life easier as an embedded developer. On ARM and other architectures, you now have devices that are described by the device tree instead of using C code. So that the device tree is a new thing, and really helped to with the adoption of Linux of Linux on the ARM hardware. And there are, of course, many more changes. It would be difficult to go through them all, of course. Oops, sorry, I clicked twice. So a few words about the Risc-V instruction set architecture. It's new. I'm not going to talk in detail about it. I'm going to give you a great reference to Drew's presentation, hi Drew, at the end, which is much more exhaustive. Here the goal is rather to show you how you can start using it, experiment with it. So just we'll focus on the technical aspect of things rather than having the whole picture about Risc-V. And this is still a presentation about embedded Linux mostly. So that's a new instruction set architecture that was created by the University of California, Berkeley, UCB, in a world that's dominated by proprietary ISAs with heavy royalties to pay, like ARM or x86. So even if you are just making the chip completely by yourself, but using the ARM instruction set, you still need to get a license from ARM. So it exists in various flavors, to 32, 64, and 128-bit variants, and it supports small microcontrollers to very powerful server hardware. So it's really likely that we'll have like PC-like hardware based on Risc-V in the next years. I hope for that at least. So anyone can use the ISA to create your own SoC and CPUs. This reduces cost and promotes collaboration. So you can have both proprietary and open source implementations. You have an open specification. People can use that to make proprietary stuff or open stuff. So it's good because precisely free implementations are being created. But in the meantime, you have proprietary implementations that are available now, such as the ones from Microchip, Western Digital, NVIDIA. So it's interesting to see both. Let me quickly check if the toolchain is still building. It's supposed to take like 22 minutes to run. So here it's building GCC essentially, most probably. So how to get your hands on Risc-V hardware? That's something new this year. You have like some hardware available. So here's what's currently available. The newest one, the new kit on the block is the Icicle kit from Microchip with the PoloFire SoC. So and an FPGA with a nice number of gates. So you can get one from Crowd Supply at $500 essentially. That's the icicle kit. Looks very nice. So it's based on a Risc-V CPU from Microchip. On the other end of the spectrum, like the cheaper ones, the cheapest ones, you can get some boards that are based on the Candroid K210 SoC, like this SidePeed MAIX bit that costs $13 at Seed Studio, so it's really really attractive. It's now supported by the mainline Linux 5.8 kernel, but its support is limited because the MMU cannot be supported by Linux. It's too special kind of MMU. You can also, so that's the one you can get. So it's, yeah, again, it's supported by the mainline kernel. You have everything you need, so you can get it and boot it. Again, you'll see more references on Drew's presentation. You can also synthesize Risc-V cores on programmable logic FPGAs. So there are many references in Drew's talk about that, how to do that, especially how to leverage open source cores and synthesize them on Risc-V on an FPGA. So before, more hardware is available next year, and actually Drew teased us a bit at the last Embedded Linux conference. So keep on listening for announcements, and at least now you can, even without waiting to get one of those boards, you can right away get started with the QEMU emulator, which actually simulates a virtual board. It's actually called Vert.io. Vert, and it's based on Vert.io hardware. So Vert.io is not trying to emulate real hardware. It just implements the functionality of the hardware without the overhead of implementing that, of implementing real hardware. So that's the latest solution in terms of CPU. You can also try it with JS Linux, by the way, from Fabrice Bellard, who's the author of QEMU, by the way. So you could try this one if you want, like X window, why not? No, well, yes, let's do that. So this is really nice. JS Linux, in case you don't know, is actually a virtual machine implemented in JavaScript. So it runs in your browser. So here we're going to emulate a Risc-V platform on your browser, as unbelievable as it can be. So here it's probably booting. Ah, yes. Okay. I didn't anticipate that my PC is also busy compiling a toolchain, so that's why it's slower than usual. Hey, there you are. That's an X desktop actually. I'm afraid I selected the virtual keyboard, so let me select. Yeah, let me select the terminal too. Was too quick. Yeah, there we are. Oh, this is emulated in your browser. That's beautiful. So you name NSA. Oh, there you are. Risc-V 64. That worked. Okay, so I stopped this because I'm slowing down the generation of my toolchain otherwise. So what we're going to build today is the cross-compiling toolchain with buildroot. So that's ongoing. We're going to build the firmware that actually is used to kickstart the operating system. We're going to use OpenSBI, and then the latest Linux kernel. Why not? It's not because there's a feature that's needed in that one. It's just I want to stay as current as possible, and this just works. And the latest version of BusyBox, which will implement the routines that we run in the root file system, and that should fit in 45 minutes. So let's see this. A bit of theory while the toolchain is building. So essentially, we in the reminder of the talk, I'm going to use the words host and target. So the host is the PC, the development PC, which contains all the development tools, and especially the toolchain to create, to compile and debug the software on the target. The target is the embedded system that we are actually building. So you have the bootloader here that kickstarts the Linux kernel, and then applications can be started, and they either directly talk to the C library. Yes, the C library is the interface to the Linux kernel. So when you open a file, for example, that's a system call, you make it through the C library. You're supposed to do that this way. So all the system calls are actually accessed. All the services of the system are actually accessed through the C library. But of course, you can go through intermediate libraries like image decoding and whatever library, database access and things like that, and then access the C library. But that's how the applications can be structured. So next, so how to build the cross-compiling toolchain. So a toolchain is a compiler, right? Essentially, that from the same source code can either, if you have a native toolchain, you generate an x86 binary, so some code that runs on your PC. But if you take the same source code, like hello.c, you with a cross-compiling toolchain like for the Risc-V target, you generate some binary that will work, that will run on a different execution machine, which is a Risc-V in that case, but that can be ARM, of course, or something else. So why would we generate our own cross-compiling toolchains? Well, compared to ready-made toolchains, you can choose your exact compiler version. As we saw, you can choose your C library, like glibc, uclibc, Mason. I'll say a few words about the C libraries. You can also tweak other features and, of course, fix bugs. So in case you find a bug and find a fix for that bug, you just apply a fix to that bug and regenerate the toolchain, keeping everything the same. So this avoids to get another toolchain that might have different bugs. So you're not going anywhere in terms of stability if you switch to another toolchain. So it's nice in terms of reproducibility and stability. One of the choices when you build a toolchain is to choose the right C library. So it's an essential component of the system, as I said. It's the interface between the applications and the system. So the system call interface is actually supposed to be accessed through the C library, right? And of course, it allows to, it's not only an interface, it also allows to implement C programs in a higher level than implementing everything by yourself. So in the case of embedded, you have three essential types of libraries. There's glibc that is found on desktop and is also useful in embedded, but it's relatively big in our standards, like 2 megabytes is big for me. Especially when I write on a boot time projects, I want the code to be as small as possible so that it loads faster, and then the system is up faster. A very popular library in the embedded space is the uclibc. It does support Risc-V 64, but the last time I checked, so I didn't check with the latest version of Buildroot, but it didn't support, it wasn't supported by Buildroot to make a toolchain yet. Especially, I mean on Risc-V 64. I'm not talking about ARM. And the other one that's supported by Buildroot to make a toolchain is the Muscle C library, which is more recent, and it is also very very nice. It's used in the Alpine Linux distribution, for example. So it's very solid and ready to use as well. So why I'm telling you all this is because you need to choose the C library at the time you create the cross-compiling toolchain. Because the GCC compiler is compiled against a specific C library, and it knows about that C library when it needs to know about that C library when compiling programs. So we have to make the choice now. My VLC is out of frame. Yeah, sometimes it is. Hopefully the presentation is still all right. Okay, so again, what we did in Buildroot is to download the sources, extract them, you run menu config, you choose the target architecture, and choose your C library, and just run make SDK, as I told you. At the end, what you have is in output images is just the tar.gz file containing the toolchain that you can expand anywhere on your system. But the thing is, toolchains contain some hard-coded directories. So there's a script that's provided by buildroot that's called relocate SDK that you just run in the place where you extracted the toolchain, and that will just take the current directory and fix up the toolchain to adapt this. So what I did was actually recorded through ASCII Nima, if you want to have a look. It's actually a way to record, in case you don't know that, it's a nice way to record text videos, so ASCII videos. Well, everything is just ASCII. So it's, look at that. And like, if I want to pause this, I can pause, and actually you can copy paste for the video. So I hope you like this. If you're new to that, just try ASCII Nima. It's a way to record your ASCII sessions in a kind of video that you can then share with people. So here, the nice thing is being able to copy paste from videos, like copy pasting the address of the buildroot tar archive. Isn't that nice? I love this one. So you can see the sequence I went through, and in terms of size, it's of course so much nicer than a real video. So just a series of strokes being replayed in that nice interface. There you are. So don't hesitate to use that. Okay. Now back to the presentation. Let's check where we are. Oh, sorry, that's what I meant. Yes. Just resize this. Yes, I just wanted to exit this actually, so see where the toolchain is. Okay, still running, still progressing. That's good. So once you have your toolchain, you can test it. So I propose to create a Risc-V 64 environment file that I can source when I want to use the toolchain and compile my project. So I'm just adding the path to the toolchain here where I extracted it to the path. And then I can test my binaries and see make sure my cross compiler, and make sure I can actually compile a file, a hello.c file, and check that it's the right architecture here. Right, so here you'll see that it's effectively Risc-V statically linked because I used -static. So here it's self-sufficient and it doesn't rely on shared libraries. So it's actually easy to test your executable with QEMU Risc-V 64, which just emulates the instruction set. It doesn't need to emulate an entire machine. And since we don't have shared libraries, it's just good to go. So my slides are ahead of me, of the actual run. A few words about the hardware emulator. So we are using QEMU. I chose to actually use QEMU 5.x because it probably has new features. But I think for the manipulations I'm showing, QEMU 4.x is probably good enough as well. So just in case you want to try, you're using Ubuntu, as I do, you want to use QEMU 5.x, just install it. It's the default version on Ubuntu 2010. But on 2004, you need to get the software from a special PPA, like a personal archive, package archive. So you'll get it this way. Oops. And you can check which machines are supported by QEMU. So QEMU system architecture actually supports and emulates an entire system, not only a CPU, but a set of devices. And the very nice thing about QEMU is that it just runs the same kernels as the kernels that support the real hardware. So that's, I mean, from my experience, it's almost always this case. So for ARM, for example, I'm just booting, when I booting an emulated machine, I just compile the normal kernel for the real machine and just boot it with QEMU, and usually it just works. So here we have a bunch of machines that are emulated. So there's the Sci5 machines, which I didn't mention, but these are the these are some boards that are not sold anymore. That were actually the first boards based on a Sci5 SoC. So I should have mentioned them in the list. They are actually a company not really making SoCs, but designing SoCs for people to use them in products. If I understand correctly, the microchip one is based on a Sci5 core or something derivative from it. There's a Spike board. It's I didn't try that one. I know Spike is an emulator as well. And there's the Vert board. So it's a virtual board based on virtual I/O devices. So you don't have real peripherals in this one, but it's easy to emulate. So let's see where we are now. Yeah, getting close. I hope so. Yes, I have to say a few things too about the way to boot Risc-V, which is a bit more specific. If you're coming from ARM, it's a bit surprising. So essentially, you have three privilege modes that are defined on Risc-V. You have the user mode, that's for applications. You have the supervisor mode, that's meant to use by the OS kernels. And then there's the special machine mode, which is for the bootloader and firmware. Like if you're running, so M would be used like for simple embedded systems, like the bare metal ones, which don't have like, you're just running code, like on good old, bare metal software, right? And that's used, yes, for the very first parts that you run on your machine at boot time, and in particular, at least when you're booting a complex OS. So that's the first stage that you need, actually, some M mode code that will kickstart eventually an operating system like here. Either you boot to boot eventually Linux, and then of course, so that's the operating system mode, let's say, yes, kernel mode. And of course, then you can run unprivileged operations, applications in the operating system. So you have three typical scenarios here. M is only M, so it's for simple embedded systems, bare metal ones. M&U, it's a variant of that, so embedded systems with memory protection between the various processes. And the more classic ones for us, at least, MS and U, so it's a Unix-like operating systems with virtual memory, as Linux will be. So let's see if my toolchain building is over now. Ah, not yet. Okay. Oh, it's building some BusyBox. That's weird. Well, we'll see. Maybe it needs some of it. So let's move on. Let's go on a little bit more and see. So now the next step is to build the Linux kernel. So I'm going to come to that soon. Hoping my toolchain creation is over now. So how to compile the Linux kernel? Essentially, you need to get the Linux kernel sources, of course, specify the target architecture. So that's where the code-specific, the architecture-specific code will be found, like where the architecture-specific headers will be found, where the hardware-specific code will be found. So it corresponds to a directory. The Arch setting corresponds to a subdirectory in the Linux kernel sources under Arch, right? So you define the Arch environment variable. You can run. You can then configure your kernel to select the features you want the kernel to be compiled. So you have a reference configuration you can apply, and then you can run make menu config and select your features. And now you're ready to cross compile the kernel if you are cross compiling. So here you set the cross compile environment variable, which is actually the prefix to your cross compiler. So if your cross compiler is Risc-V 64-Linux-GCC, then the cross-compiler prefix is everything before GCC in the name. That's how it's done, because the Linux kernel makefile is going to invoke cross-compile GCC, and then you can run make, and you have your kernel binary that's ready. Then you can also install modules with make modules install, or install the kernel with make install, or do a manual copy. So I hope my compiling is over, because we may be getting late otherwise. Oh yes, that was a bit slower than expected. Okay. So let me, oh, I forgot to copy actually a hello.c file. Let me get one. Oh, I can actually copy it, I think. So let me do that in another window that you won't see. Or you may see, I don't know. Okay. Yes, you see it. Okay. So cp hello.c to my machine. So I'm using two machines actually too. Ah, okay. Well, no, right, wrong syntax, my mistake. Ah, okay, I didn't install the SSH server. Just a minute. If I can find the right window, yeah. So that's the one thing I forgot to prepare for this talk. Okay, good. Right, so now the copy should work. Okay, not yet. Okay, let's make a manual copy then. That's life. Okay. Okay, insert my key. Just a minute. Okay, there we are. So back to the window. Yeah. So the first thing I said I need to do is to extract the toolchain. So I'm gonna be here in toolchain, for example. Well, actually in Risc-V. Let's do that this way. Toolchain. I'm going to extract the toolchain. So it's in build root, output images, right? So it's this. And as I said, there's a relocated SDK. SH command. Right. Okay, good. So you see in bin, you have all the executables here corresponding to the toolchain. Okay, so I get back to Risc-V, and I'm going to say what I, sorry. Hey, I'm going to create an environment file. So let's actually grab it from the slides. Like this one. So that's something I'm going to source every time I need my toolchain. Right, so I source that. What? Okay. Okay, and now I can try to compile. Oh yes, hello, the hello.c program, and see. So it's called Risc-V Linux GCC. So static, it's easier, minus hello and hello.c, and see what we get. Hello, yes. So it's a Risc-V statically linked. I can actually try to execute it now with QEMU, as I said, QEMU in user mode. And it works, right? So now it's time to quickly get the Linux kernel, otherwise we may be late. It takes a bit of time to compile it. So kernel, you get it that from kernel.org. Here's the one. Yes. I like to copy and paste, copy the link location to from the browser to the terminal. That's easier. It's sad that they're shipping the release candidates only in GZ TAR-GZ mode, so it's a bit like slower to extract, to download and extract. So now I'm extracting the kernel sources, and now I'm getting back to the slides. So I actually need to set the two things I told you, like cross-compile and Arch. So I'm going to add those. Oh, sorry. I can copy and paste while I am in full screen mode. Right. So just need this. There we are. So I'm going to source that again. Now I can go inside the Linux kernel sources, and I'm going to apply the default environment. So I'm just doing that right here, make dev config. And compile it quickly with make -j8. So it's going to run for 5 minutes or something like that. So in this, I'll have time to explain what I'm doing. So yeah, that was already explained. So yes, you can see the available configurations. The Linux kernel gives you some ready-made configurations for various boards or various SoCs. So here, you can just run make help grep dev config, and you'll see the default ones. Except those two, like save dev config is a special one, all dev config and all dev config are special ones. But otherwise, you have like support for the Candroid 210 board in 2 different modes. Plus the RV32 one, which I don't really know, but at least I checked with the default one for Risc-V, and it just works. So that's what I did. And we could further customize the configuration with make menu config, which actually we don't need here because it's just fine. So we run make to compile, or make -j, like jobs. It runs multiple jobs at the same time because compiling the kernel is just like turning lots of .c files into .o files. So that can be parallelized massively. You can even recompile if you keep keep recompiling the kernel over and over again. You can also use C-cache. It's a compiler cache that also makes it even faster to recompile the kernel over and over again. So you could use that too as a nice trick. At the end, you get 2 files. Essentially, well, the compiled kernel in ELF format. So that's something you can feed to a debugger. That's not ready to be executed, but that can be fed to the debugger. And then you have in Arch, Risc-V boot, you have image. There's an uncompressed kernel, and image.gz. That's the compressed kernel you can boot. Well, you could boot image as well, but it's nice to have the compressed kernel. It's sometimes faster to load. Let's see. Oh, sorry, no, not this. That's what I want here. So let's see how it looks like on the kernel side. Kernel compiling could be over. Not yet. Yeah, it takes a bit of time. So the next thing we need here is to actually compile the firmware, because you can't, unlike on ARM, you can't directly boot the Linux kernel from QEMU. It doesn't work. It's because you have to switch. You have to start the machine in machine mode first, and then jump to S mode. So this is done by some special software, by some special firmware. So there are various projects. The last time I used another one like BBL, Berkeley bootloader. Now I'm using OpenSBI. So that's what you need to use here. So you and the SBI allows it effectively to boot from M mode to S mode. It's called Open Supervisor Binary Interface. So the SBI is a standardized way of invoking an OS from the supervisor. So you clone that actually from this project, and when you make it, actually you include you kind of embed the S mode image that you want to build, like the kernel binary that you want to execute. So at the end, what you get is a firmware payload. So like the firmware code plus the payload, which is the Linux kernel, which is then a binary that QEMU can boot, which is not possible, unlike on ARM. Again, it's not possible to boot the kernel directly from QEMU. So to boot the kernel now, we're going to use QEMU, right? So passing those options, so passing just minus kernel and the payload here and the console, right? Some console setting to tell the Linux kernel. That's an argument to the Linux kernel here to redirect the booting messages to the right place. So let's see. I hope it's over now, because I was a bit optimistic in the time it was taking to compile. Maybe the thing is probably because I'm using the camera, it slowed down compiling. So that's probably the reason why. Anyway, I can move on explaining things about the root file system. So here, when you boot your board, you'll see the kernel booting, but at the end it will panic because it doesn't have a root file system yet, and that's what we're going to fill. So that's the next step. And by the way, if you start QEMU, we were told we were shared that information with one of our participants to our courses. You can actually interrupt QEMU with Control A followed by Control X. So it's very convenient to stop QEMU. Before that, I had to kill it from another window, which was really inconvenient. So to build the root file system, we're going to use some software that's called BusyBox. So 10 years ago, it was implementing all those commands, which was already nice. But now, whoops, it's even more. So all the commands you may dream of in your scripts, essentially, in the command line scripts that you would start in your machine. Like, yeah, everything you need is there. So to download BusyBox, you create a root file system installation directory, you download the sources, I'm going to show you that, and you extract the archive, and then you add, I start by selecting nothing, so I prefer to have like a minimum set of applets. Applet is the commands that BusyBox supports. And then by running make menu config, you can choose to build a static binary, you can choose to pass the cross-compiler prefix, that's in the configuration this time. And then you can choose where to install BusyBox, so like in our rootfs directory, and then we select the commands that we want to execute. So I hope the kernel compiling is over. It's not. Okay. Well, actually, I can prepare the QEMU emulation here, the QEMU script, to save a bit of time. And I also need to compile OpenSBI. I forgot about that. So let me open a new tab. I'm going to call it QEMU. All right, so file. So I'm exceeding the 45 minutes, I'm sorry. Right. I make that executable. Okay. I need to compile OpenSBI2. So I need to clone that. There we are. Well, I don't have the kernel binary yet, but it's coming soon. Right? Yeah, that's the next kernel. Hey, come on. Yeah, I'm sure that's the camera that slows down things a bit. Let me go through the slides anyway. So there's never any waste of time. So yes, we'll eventually populate the root file system with BusyBox. So when you install BusyBox, you see that actually there's only one executable. That's here, BusyBox, which is it fits in 300K here. And all the other executables are links to BusyBox. So when you invoke, for example, mount, it's actually BusyBox that gets called, but it checks its name. So if it's invoked with the mount name, it knows that it should behave as mount. That's how it works. So that's what happens when you run make install. So I find it quite funny because we're actually using a 64-bit system to boot a 300 kilobyte program, to run a 300 kilobyte program. It's find it funny. Now, and then we can put that in a file system, in a file system image. So we create an empty file with 1 megabyte size, so one block of 1 megabyte, so it's 1 megabyte. We format it as if it was a real partition. We can format a file system image. And then we actually create a mount point, we mount it with -o loop. It's a way to mount a disk image in a file to a mount point. And then we can populate the content, what was installed with BusyBox, we can replicate that in the mounted image. And every time we make an update to that, we just run sync. So let's go here. I hope that the kernel compiling is over. Yes, it is. Good. So you see it did create my image.gz, as I said, as I promised. So now, oh yeah, I should have copied the command because I don't remember it by heart. That's the one I want. Copy. Yes, that should be right. Nope. Maybe because why Arnix? Oh, that's weird. Okay, did I source the environment? Maybe not. Yeah. Right, it's the wrong environment. It's this machine is still configured for ARM, I believe. Make clean. It's going to be better. Yes. Right. So now I'll be ready to run QEMU. Yeah, the payload.elf file is created. So now I can try to run QEMU. Okay. Yes. Okay, I haven't installed it yet. So well, let's do that without MISC. I think it's QEMU MISC. Now, let's see my notes. Well, let's do QEMU system MISC. I think that's enough. So I'll use this one, QEMU system MISC, without having to use a special PPA. So it's the emulation of the various systems that are supported by QEMU. And this will confirm that QEMU4 does work. Yeah, so it's booting. You see the bootloader. But not more. Okay, so maybe I need to use the QEMU 5. Indeed. I'm missing. And this one. Okay. It's going to be installing QEMU 5 now. I just want to show that the kernel boots at least, because we are very slow, very slow, but very close. Okay, QEMU. No, so I must have done something wrong in there. But I don't know exactly what. Compared to the so many times I actually ran it. Is it OpenSBI here? Well, okay, well, never mind. The instructions are supposed to work. If there's something that needs fixing, I'll figure out and fix the instructions. It's a bit of time to wrap up anyway. There we are. So you can just follow the instructions. Apologies for this. I underestimated the time to build the toolchain. So if you follow this, we can then create a device directory to see all our devices. We add mounting of proc and sys, and then we can start some scripts automatically using BusyBox init, which allows to specify some scripts to be run at boot time. So that's how it works. And then we can even start an HTTP interface. So we're setting up networking between QEMU and the target, QEMU and our host here. So we're adding some networking capabilities like this. And then you can go to, I can add a simple script here that's going to be evaluated by the BusyBox HTTP server, showing you the uptime of your system. So that's a way to interact with your machine with HTTP server. So you can just go there, visit the link, and you're good to go. So I'll make sure I'll fix what was wrong in the command I typed. It just was working all the time. So the next steps, what I wanted to do is actually start booting Linux from U-boot instead of directly from the firmware. And I'm close. That's a bit disappointing because I wanted really to show you U-boot as well. So I actually reported that to the software development mailing list for Risc-V. So I'm explaining what works. So what works is this, you were supposed to see. And then trying to boot with U-boot and then Linux. And this just works at the beginning, but when I start the kernel, I end up with some errors here after adding the right debugging messages. So it kind of starts, but then boom, something is wrong. So I still need to investigate that. But then in the next version of this talk, I'll be able to show both U-boot and the Linux kernel. I mean, the Linux kernel being started from U-boot. So what to remember, embedded Linux is easy. It makes it easier to get started with Linux. Just a few steps and you're good to go. You have a command line. Believe me, you didn't see that. Sorry, but it's just a few steps away from, just a few things to type and you're good to go. Risc-V is a new open instruction set architecture. I really invite you to use it and support it. Yeah, and the nice thing about investing in embedded Linux knowledge is that things don't change so much over time. So you just get more features, more hardware, more possibilities. So to finish that, I highly recommend to have a look at Drew's presentation about the latest presentation at about Risc-V. So many aspects: hardware, introduction to the platform, the hardware, how to make your own. It's just an unmatchable presentation. It's so crystal clear. I'm amazed how Drew can cover so many aspects in less than an hour. Unlike me, as you see. So if you want to know more about embedded Linux too, you can go and check our freely available slides about embedded Linux. And you have only presentations and conference presentations from Bootlink here. And last but not least, you have the embedded Linux wiki, where you have a bunch of resources on all types of aspects. So if you're looking for a platform where to share your knowledge or where to learn from as well, you could use this one. Right, thank you. Sorry for the overtime. Thanks, Gert. See you. Thank you all. So I don't know whether I can stay and ask question if I'm allowed. Any maker board instead of QEMU? Some are coming. Cannot say more. So you just look at Drew's presentation. You'll have like interesting boards that are coming up in the next, either at the end of this year or early next year. So there will be a lot to work with. Yeah, you'll have a. Oh yeah, Yocto can be used as well. It supports asking a question, answering a question from Joao. You can use Yocto, of course. Just Yocto is slower, so it doesn't fit in 45 minutes, at least for the first run. That's the reason why. But yes, of course, you can use it. In 45 hours. Yeah, the one is just $13, so it's really nice. It's great to hack. Thanks to remind us, Drew. I tried. Yeah, hi Christian. I tried CrossToolNG. Well, I haven't tried recently. I guess it just works well. CrossToolNG is a tool to generate toolchains and only that, so it does it very well. Thanks, Drew, for the link. Yes, Murat, I agree. They have a bias towards Buildroot. Yeah, I'm not completely neutral here. But I don't always use Buildroot. Like as I showed, when I need to root file system to boot my system with, I just get BusyBox, menu config, just install a few executables I need, and then compile my kernel, and then I have something to boot my kernel with. I don't use Buildroot for like this. So if you once you get familiar with that, you can quickly, in a matter of minutes, you can get a root file system with some default commands and boot on that file system. You don't even need Buildroot. Okay, a question from Selva Kumar. Jumping straight into device driver development for Risc-V boards, is it a good idea? Well, if you have a board that boots, I would say yes. If you don't have to mess up with the understanding how to boot that particular kernel, you have a kernel up and running, then you can add drivers. That's more than welcome. Effectively, that will broaden the support for the architectures we want to support. So I would say yes, and the Linux kernel does its best to keep the architecture-specific details hidden. So yes, you can go and try to implement driver development for Risc-V boards, especially if the initial support for the board is already there. There's a new link about Buildroot. Yeah, okay. For building it with for the K210. Yeah, good. Well, so I'm really excited about the progress of Risc-V. It's going to change lots of things. So you'll be able to make your own. You can participate to open source projects for SOCs or for FPGAs. That's really exciting. So, well, thanks for your participation to this talk.